Hey there, in this video we're going to continue our study of Chapter 9, moving on to Section 9.2, comparing two groups, and we're going to look at the quantitative response. So we're going to be looking at the difference between two means. And the first case that we're going to take is when we know the population, when we don't know the population standard deviations for each of them, because that is the usual case. It's very rare that we know the population standard deviation. So we're going to look at the t-test first. So remember, when you don't know any of the information from the population, we use the sample t-test. And so we're going to be looking at our t-tables. When you are given a population standard deviation, that's when we use the z-scores. So in this case, we don't know population standard deviation, so we're going to use the t-scores, so the t-test. And so our hypothesis is going to be that the difference, so mu1 minus mu2, is going to be equal to 0. So a two-sample t-test is used to test the difference between two populations, and so we're going to usually assume that it is 0. And the first thing is always, as you read a problem, make sure your sigma 1 and sigma 2 or any standard deviation, is it given to you? Do you know the population standard deviation, or do you not know? So since we're doing a sample t-test here, using t-scores, we're going to make sure that sigma 1 and sigma 2 are not known. We want to make sure also that the samples are random, so simple random samples, and that the samples are independent. And we want to also make sure that the populations are normally distributed, or that our samples are more than 30. So this part, we're essentially checking the conditions of the central limit theorem, so that then we can use our test statistic or standardized statistic. So our sample statistic is going to be the difference in the sample means. Our standardized statistic is the sample statistic minus the population parameter, which we oftentimes assume it to be 0, divided by the standard error. So the variances divided by the samples of each. So this will be something that you want to put on a note card somewhere, or your 8.5 by 11 sheet of paper that you'll be allowed to use on tests. So just a note about independent. What does it mean for samples to be independent? And so we talked about it last time in section 9.1 with the proportions, but I wanted to give a little more as to what does it mean to be independent. So our sampling methods: independent samples means that the sample selected from one population is not related to the sample selected from the second population. So usual examples of this will be if you're testing something on like say cholesterol levels in males versus females, right? So then the males and the females are not, they're not related. So one population is men, the other population is women. Dependent samples, or pair or match samples, is each member of one sample corresponds to a member of the other sample. So going back to my cholesterol type of example, a dependent sample will be, say you test cholesterol levels in a group of people, say in females, prior to an exercise routine. So somebody wants to test the effectiveness of an exercise routine to lower cholesterol levels. So you will take a sample of, say, females, and then you would test their cholesterol levels. Then they'll go through the exercise routine, and then at the end you test their cholesterol levels again. So that will mean that, right, it's the same population, it's the same women that were used in the sample, or it doesn't have to be women, it can just be people. So that will be things that are dependent, because you're using the same subjects from the same population, rather than independent samples. You have two different sets of observational units. And for here, in this two-sample t-test, we use the degrees of freedom are going to be the smaller. You take the sample with the smallest number, and then you do n-1 from that. And remember, with the t-test also, you always round down. So let me bring in the t-table. We've done examples in the past that if you have, like, say, 72 people in the sample, your degrees of freedom will be 71, but you always round down, right? So we will go to 7. If you had 136, then you will go to 100. So you always round down. And so it makes sense then that when we have two samples, that we're going to take the smaller size, because you don't want to assume that you have more people in the other sample than you do, right? So you're always going to take the smaller sample and go with that one. And then if we're going to use the confidence interval method to decide whether to reject or fail to reject our null hypotheses, then we use the usual format is your sample minus the standard error, and then the sample plus the standard error is your upper limit, lower limit, and then the population parameter is in the middle. And the margin of error in this case is based on your significance level or whatever confidence interval you want. Like if you wanted a 95% confidence interval, then alpha is 0.05, so you will do 0.05 over 2 and find that on your t-table and then do our error. Okay, let's try an example. YouTube TV versus Hulu. So both YouTube TV and Hulu Plus Live TV have their perks, and Hulu Plus Live TV has made some changes to give YouTube TV some considerable competition. To compare customer satisfaction levels of two competing cable television companies, I really should have said streaming services, 174 customers of YouTube TV and 355 customers of Hulu Plus Live TV were randomly selected and were asked to rate their services on a 5-point scale, with 1 being least satisfied and 5 being the most satisfied. The survey results are in this table, and we want to know at the 1% level of significance whether the data provides sufficient evidence to conclude that YouTube TV has a higher mean satisfaction rating than Hulu. And we're going to use the p-value approach. This is a t-test, so we may do the critical region and the p-value approach together. Sometimes the critical region is more helpful with the t-test. So let's see. So what do we do? So oftentimes, right, you get a problem like this, you read it, and then now what? So we're going to focus on the question, at the 1% level of significance, whether the data provides sufficient evidence to conclude that, okay, so there's our claim, to conclude that YouTube TV has a higher mean satisfaction rating than Hulu. So this is the claim that we're studying, whether YouTube TV has a higher mean satisfaction rating. So let's see, based on the data, YouTube TV, the mean is 3.51, and for Hulu, the mean is 3.24. So it does appear that YouTube TV has a higher average rating, but let's now go through the test of significance. So the steps to follow, as we did before: verify that the samples are random and independent, verify that the central limit theorem is met. In this case, we want normally distributed population or samples are more than 30. And in our case, our samples, the size of the sample here is 174, here's 355, definitely more than 30. So that one is check. Are they independent? Right, independent, let's go back to here. We want them to look like that. And yes, because we have YouTube subscribers, YouTube TV subscribers, and then Hulu subscribers. And so we can say they are independent. If you were running this study, so it doesn't say here, but at some point we will probably say any people who had both were excluded from the study. So that will be like a disclaimer at the end. You could say like, because some people might have YouTube TV and Hulu, and then so we can say, well, those people were not included in the study. You either have to have just YouTube TV or just Hulu in order to participate in the study, because then that will make it independent, right? We don't want the populations we don't want to be able to match them. So matching them, that's sorry, I keep going back, will mean that one person, you see their rating for YouTube TV, and then that same person, you see their rating for Hulu TV. So we don't want to be able to match them like that. So in our case, we can say that they are independent. So this one is, we can put a check mark on that, let me see, how can I do that? All right, so we can put a check mark on that. Verify that the central limit theorem is met. Normal distributed population, or our samples are more than 30. Samples are more than 30, so yes, so we can put a check mark on that. Specify the level of significance. So we are told test at the 1% level of significance. So we can then restate that. So level of significance will mean alpha equals 0.01. 1%, right? Convert that to a decimal, so alpha is 0.01. So that's our level of significance. Now state the claim mathematically and verbally. Identify, so what this means is identify the null and alternative hypotheses. So what is our claim? Here, let's see, conclude that YouTube TV has a higher mean satisfaction rating than Hulu. So which one is this, the null or the alternative? Right, usually in the problem you'll be given one, so I usually go for like, okay, which one is given, and then write that one down and then go back and find the other. And so this, because it says higher than, right, a higher mean, so this is the alternative because it has no equality in it. So this is the alternative. So the YouTube TV has a higher mean satisfaction rating than Hulu. Based on the data here, X1 is YouTube and X2 is Hulu. So our alternative hypotheses, we can just copy it from up here and we can say YouTube has a higher mean satisfaction rating than Hulu. I probably don't want to highlight it though, so there you go. YouTube has a higher mean satisfaction rating than Hulu, and then we can write that also in symbols. So how do you write it in symbols? So we'll have a H sub A, and then we can write, so what does it mean for YouTube TV to have a higher mean satisfaction? So that will mean that mu1 will be bigger than mu2, but that also means that their difference will then be greater than 0, right? If the YouTube rating is higher in the population, then when you do mu1 minus mu2, you're going to get a positive number. So this is one way to do it. You could also just say, instead of the minus there, you can say mu1 is greater than mu2. So those are two ways that we can write the alternative. And so now that we have the alternative, we can go back and write the null hypotheses. So the null hypothesis will be, so here there is a difference, right? There's a positive difference. So the null hypothesis will be that there is no difference between the mean satisfaction rating between of YouTube TV and Hulu. And how do you say that in symbols? We'll have our H sub 0, and then if there is no difference, that means that they are the same, or that the subtraction, the difference between them is 0. So we will say mu1 minus mu2 is equal to 0. Now remember, the null, the hypotheses, the null and alternative hypotheses are always written about the parameters. The parameters are mu. The sample is the x1, I guess that should be a bar in there, x1 bar and x2 bar. So the hypotheses are always written about the parameters. In this case, because we have a quantitative variable, right, average rating, it's a score, a number, then we use mu. In section 9.1, when we were doing it with two proportions, our parameter was p and our sample was p hat. And so in here, or, right, you can say mu1 equals mu2. So instead of minus mu equals 0, you can say mu1 equals mu2. But the 0 just helps us for when, especially when we're doing confidence intervals. All right, so these are our hypotheses. Now the alternative is the one that we really like to focus on, because the symbol used in the alternative tells us what? Gives us some pretty useful information, right? The symbol that we have here, that tells us that we have a right tail test. So always pay attention to the symbol that you have in your alternative. If it was less than, it will be left tail, and if it was not equals, it will be a two-tailed test. So as soon as you write your alternative hypotheses, notice which direction the symbol is or what the symbol is, and then write what that means. So that means we have a right tail test. So when we find our standardized statistic to find the corresponding p-value, right, that's where we need that, a right tail test. It means we're going to be finding the area to the right of our test statistic, or of our, sorry, a standardized statistic. All right, so now let's go find the standardized statistic. We're going to use this formula to find our standardized test statistics. So let's go to my notebook. And so I just rewrote what my null hypothesis is and my alternative hypothesis in symbols because I need that for my p-value and for the confidence interval. So here's our test, or T, for our standardized statistics. So let's find our sample statistic. So we need to find x1 minus x2 bar. So x1 bar minus x2 bar will be based on our sample here. So x1 is 3.51 and x2 is 3.24. And so when we do x1 bar minus x2 bar and you subtract those, you get 0.27. And right, our x1, we're calling that YouTube TV. And this is Hulu. So that's how I looked up the data. So YouTube TV and Hulu. So it's 0.27, so this is our statistic for the sample. And so our T, now we're ready to find the T. So T is going to be our test statistic, so 0.027 or 0.27 minus our population parameter. What are we assuming mu1 minus mu2 is? This comes from where? This comes from our null hypothesis. What are we assuming it is? Mu1 minus mu2, we assume it to be 0. So then that's going to be minus 0 divided by, and then the square root of S1 squared. So let's look at the data again. So S1 is 0.51 and S2 is 0.52. So this is going to be 0.51 squared over N1. How many subscribers in YouTube TV? 174. So 0.51 squared over 174 plus 0.52, is that what it was? Square over the number of subscribers of Hulu. So we had, yep, 0.52 and then 355 Hulu subscribers were surveyed. And then we put this on our calculators very carefully. Make sure you use lots of parentheses. So 0.27 divided by, and then square root, parentheses, and then put that in. And what I got was 5.68. You run around to 2 decimal places because that's what we're going to look up on our T table, right? This is a T test. So we're going to look at the T distribution. And so in order to look at our T distribution, we also need our degrees of freedom. So what are going to be our degrees of freedom? We are going to pick the smaller of N1 or N2. So the smaller sample size, I have 174 or 355. So we're going to go with 174. So degrees of freedom, remember, is N minus 1. And then we're choosing the smallest sample. So we're going to use 174. So this is going to be 174 minus 1. So our degrees of freedom is 173. And so when we go look up at our table, we're going to look degrees of freedom 173. And remember, the alpha level of confidence was 0.01, right? 1% level of confidence. And so what I said we were going to do them together, the critical region and p-value method. So that means that when we have our bell curve, because alpha is 0.01, that means we're going to go somewhere over here, and this is, we want that to be 0.01, 1%. So this area here is 1%. So when you look up your critical value here for t, that's what we're going to do. So let's go to the t table. And because we're just doing a right tail test, we look at the area in one tail, so 0.01. So there's our level of significance, 0.01. And we want 173, we said. But notice that here it goes from 100 to 200, and we always round down. We always round down because you're talking about sample size. So you don't want to, I know normally in math we round up, right? 173, you will round out to 200, round up to 200, but that's not what we're doing in here, because here you're saying that's the sample size. So those are the number of people you surveyed. So you don't want to go from 173 to 200. You're saying you surveyed more people than you did. You don't have that kind of data, right? You don't have that extra set of data that you, if you round it up to 200. So you always want to go on the side of caution and round down. You don't want to say that you have more people that you surveyed than you actually do. It's better to say you have less, and so you round down. So 2.364 is our critical value for a 0.01 level, critical level. So going back to our notes, so this will be, so we put our critical value there for t. So 2.364 here. So this is then, this is the rejection region. So let me see what color. So let's put that in here. So this is the rejection region. Now let's look at our t value was what? 5.68. So where is 5.68 fall? Does it fall in the critical region, the rejection region, or does it fall outside of that? 5.68 does fall in here. So is in the critical region. Can't spell. Which is the rejection region. This is a right tail test. So if you were using a left tail, you will be looking at values over here. If you were using a two-tailed test, then you would do it a little differently. But so this is what we're doing. And notice that if we, when we go back to our table, our t value was 5.68. It doesn't, those values aren't on here, so I can't actually find the p-value for 5.68, right? Notice that it doesn't really give me that kind of value. It doesn't give me the area, so I can't use the p-value method with this table. So that's why I wanted to do essentially both the critical region, and I did say the p-value, but we can use StatCrunch to find the p-value. So the table doesn't help me find the p-value associated with 5.68, but we're going to use StatCrunch to find the p-value. Now, because this is a right tail test, that means that our p-value, we want p-value will be the probability that t is greater than 5.68, right? And that's because we are using a right tail test. But our table, if we were able to look at the table, it doesn't give us the t greater than. It gives us the area to the left. When we look it up here, right, the critical value is giving us the area to the left in here, but we want the area to the right. So this is going to be 1 minus the probability that t is less than 5.68. So that's what we would be looking if we were able to get our value from the table. This is what I will do. So now let's go to StatCrunch and let's put in our information. So we probably have to bring in this, our entire table, to be able to put it in StatCrunch. So go ahead and open up StatCrunch if you don't have it already open so you can follow along, and I will write up the instructions. As we go to StatCrunch, these are the instructions we're going to follow. So click Stat in the top menu, then select T-Stats because we're using a t-test. If we were using the z-test, then you will use C-Stats. And then you're going to select To Sample with Summary from the submenu. And then we're going to enter our data, mean, standard deviation, and sample size for both samples. And then we're going to select the hypothesis testing, and we're going to look at our null and our alternative to be able to enter the proper information. And then we're going to come back for part B and do the confidence interval. So what we're going to need for StatCrunch is to keep this handy. So if you can open up a new window that has this, so you can look at it as we go. So let's go to StatCrunch. So when you open up StatCrunch, we're here. So looking at our instructions, if you have another window, or if you wrote them down or do a screenshot, we're going to go to Stat, go to T-Stats, and then To Sample with Summary. If you had data that you pull up, like some homework problems, you may have that little window thing, little icon that says click for the data, and then you can copy the data and put it in StatCrunch, and then you have your data here. Then you will do a t-test with, or t-stat with data. So let's go back to t-stats, To Sample with Summary, because we don't have data populated here in our table. So with summary, and then we're going to enter our information. So our sample mean for sample 1 is the YouTube TV subscribers. So our sample mean there was 3.51. The sample standard deviation was 0.51. And we had 174 subscribers. Our sample mean for the Hulu, so sample 2 is what we call Hulu. So Hulu, the mean was 3.24. The standard deviation was 0.52. And for Hulu, we had 355 subscribers. And we want to do a hypothesis test, right? So here is like, what do you want to do? A hypothesis test or a confidence interval? Right now, we want to do a hypothesis test for mu1 minus mu2. Our null hypothesis is that it is equal to 0. Our alternative hypothesis is that mu1 is larger than mu2. So when that's the case, mu1 is larger than mu2, that means that this difference is going to be greater than 0. Or you can also think that we have a right-tail test, so this should be a greater than. And show critical value. We want at the 0.01 level of significance, right? 1%. And click compute. And so this brings us our result. So we have, make sure that you compare there your null and your alternative hypothesis. Make sure that that is what you had selected. And so here our sample difference, 0.27. Remember that is what we got. Going back to our notes, we had gotten 0.27 for our sample statistic, and our standardized statistic, or t-score, is 5.68. So what did this give us? T-statistic 5.68, or critical t-value is 2.33. This is for the critical region. When we did the critical region method, we got, where is it? we got 2.364. So StatCrunch is more accurate, right? Because it's using the actual 173 degrees of freedom. We used 100 because the table didn't give us the values between 100 and 200. So, but StatCrunch gives us a more accurate critical region, but they're still pretty close. Now notice our p-value. So this is what we want. The p-value is 0.0001. So that's what we're going to focus on for us to make a decision whether to reject or fail to reject the null. So let's note that p-value. I'm going to copy it and bring it back to our notes. So our p-value, we got it to be 0.0001. So we have 0.001 from StatCrunch, and so now we compare with our alpha, and you make the decision. How do we decide what to do? So you compare your p-value with your level of significance. So to make a decision about the null, compare the p-value versus alpha. Or p-value, we found it to be 0.0001, and alpha we know was given to us as 0.01, 1% level of significance. So what do we do? Reject or fail to reject? Which one is smaller? Our p-value is smaller, right? So when the p-value is smaller, then we reject the null. So we reject the null hypothesis. So that means we are rejecting the claim that the mean satisfaction rating of YouTube TV and Hulu subscribers is the same, that there's no difference. And so we have strong evidence to suggest that the Hulu subscribers have a higher average rating of satisfaction than Hulu. So put it in the context of the problem, right? To put it in the context of the problem, it's helpful to go back to when we wrote the null and alternative hypothesis in words. And so when we reject the null, we're rejecting that there's no difference between the mean satisfaction rating of YouTube and Hulu. And so that means we have the data suggests that we have strong evidence to support than the alternative, that YouTube TV has a higher mean satisfaction rating than Hulu. So when you write it in the context of the problem, then we can say the data provides sufficient evidence at the 1% level of significance to conclude that the mean customer satisfaction for YouTube TV is higher than that of Hulu. So something along those lines, right? It doesn't have to be perfectly like that. You have to write it in your own words. So make it yours. How would you say we have sufficient evidence to accept the alternative, right? You reject the null, you accept the alternative. And it doesn't mean that the alternative is true. It's just that we have strong evidence to suggest that it could be true. Now, part B is asking us to construct a 99% confidence interval from mu1 minus mu2 to test the same claim. So this is a little different than what we did last time, right? If I wanted to go with the same 1% level of significance, and because this is a right tail test, if I wanted to go just from part A rolling into part B, well, not part B, I don't want to confuse you, but if I just go from here, test at the 1% level of significance, if I do the p-value or the critical region approach, then I can use this. If I go to the confidence interval approach for this right tail test, I would actually be finding a 98% confidence interval, right? Because as we talked about in the previous video with the two proportions, when you have a right tail, then you truncate it here 0.01, but a confidence interval needs an upper limit and a lower limit. So I need to then, by symmetry, recreate that over here, which will give me 1% here and 1% here, so 2% total, leaving me 98% in the middle. So that will be a 98% confidence interval. This is different. I'm essentially unrelated to part A, except for the same data. We're going to construct a 99% confidence interval from mu1 minus mu2. So if I wanted to go back to on our notes, I gave you what the confidence interval was. So if you want to do this by hand, you need to compute the margin of error. And the margin of error is given by, so we will have to find our T alpha over 2, right? So 99%, so that means alpha is 1%. So you will be doing 0.01 over 2, so 0.005. And then look up that in our t-table and then multiply by the square root of this, or we can go and use StatCrunch. So let me use StatCrunch just to show you. Because I have the data already loaded here, I'm just going to go to options and edit so that I don't have to enter the data again, right? I already have my sample 1 data there, my sample 2 data there. So I'm just going to go from perform a hypothesis test to a confidence interval. And the level of confidence is 99%. So do 99 and compute. And so this gives us our lower limit and upper limit. So 0.146 and 0.393. So that will be our confidence interval. So let me write that in our notes. So 99% confidence interval will be 0.147 is our lower limit, and this is for approximating the population parameter, so mu1 minus mu2, and then the upper limit was 0.393, looking at our StatCrunch data. So now how can I use my confidence interval to make a decision about testing the claim? Do I reject the null or fail to reject the null? So how do we decide that? So the question to ask yourself is, does the confidence interval contain the null hypotheses, the null estimate? What was our null? Our null hypothesis is that, we wrote it somewhere, that mu1 minus mu2 is equal to 0. So, right, so we can write that over here. The null says mu1 minus mu2 is equal to 0. So does the confidence interval contain 0? That's really what we're asking. So does the confidence interval contain 0? And 0.147, 0.393, so we can say no. So because the null hypothesis is not in there, that means we reject the null. At the 99% confidence level. So that means that we are 99% confident that the null is not in here. And notice that since these values are positive, that means that mu1 is greater than mu2, because it doesn't go from negative, right? There's no negative values here. So that means when you subtract two things and you always get positive, that means that the first value is larger than the second. Otherwise, right, if mu2 was at some point larger, you will have a smaller value, say like 2 minus 4. That will be a negative number, which that's not the case here. So that means that mu1 is always larger. So that means that the average rating for YouTube subscribers is larger than the average rating for Hulu subscribers. So p-value, critical region, and confidence interval, we get the same result. We reject the null, and then you can go back and write the same thing. So the data provides sufficient evidence at the 1% level of confidence, or you can say using a 99% confidence interval, the data provides sufficient evidence to conclude that the mean customer satisfaction for YouTube TV is higher than that of Hulu, because you get positive values for your confidence interval. So that's how you do all three: p-value, critical region, and those go hand in hand, right? Notice how essentially this is the critical region, which is the rejection region, is what's shaded. So if your standardized statistic falls in that region, in the critical region, then you reject the null. And when you're talking about p-value, right, 0.01 is the area here. When you get our p-value, which is smaller than alpha, that means that then the area is contained within the rejection region, the critical region, and so you reject the null as well. And the confidence interval method is more about is your hypothesized parameter. So in this case, our hypothesized difference in the means, is it contained in your confidence interval? If it is, then that means you fail to reject the null. If it's not, like in this case, then we reject the null. And that means we accept the alternative. So going back to the notes, we finished that example. And the last thing here is that alternate methods assume that alpha 1 or sigma 1 equals sigma 2 and pool the sample variances. So if sometimes you may be given, even though you're not given what the standard deviations are, if anywhere in there it says assume that they're the same, that means you will pool the sample variances. And so if you do it by hand, what changes in your in your test statistic is that instead of doing S1 square and S2 square, you do the pool variance. And this is the formula for the pool variance, which is not very pretty. If you want to do it by hand, go for it. Notice your degree of freedom are the sample sizes added up, and then you subtract to essentially the degrees of freedom for each sample added up. And so I'm not going to go through it because this is going to take really long, but in StatCrunch, you can still do it in StatCrunch. If I go over here to edit and I go back to hypothesis test, notice here calculation options, pool the variances. And so now it will calculate it with the assumption that the standard deviations in the two populations are the same. So if you see anywhere in the homework or in other places that assume that the standard deviations or the population variances are the same, then you will come here and just click that button and it will give you the pool, the p-value for the pool variances. I couldn't think of the word. And yeah, so that's the only thing. So this, at least to me, seems a lot better. Just click a button and have a computer for you rather than doing all this by hand. Of course, if you don't have access to StatCrunch or StatDisk also does it, and in your homework in my lab, I put a video on how to use StatDisk to do the same thing. So if you prefer StatDisk, then you can use that. And then if you prefer StatCrunch, this is how you do it. Now, for the last thing here, I just gave some exercises I want you to try on your own and practicing with independent and dependent samples. Are they dependent or independent? And then kind of try practicing testing the claims. And so notice this one is assume that the variances are the same. So then you will go into StatCrunch and just click that little button that says pool the variances instead of doing it by hand. If you want to do it by hand, by all means, go ahead. And this is the pool variances. This is how you would find it. And the other thing is that if you know your population standard deviations, then you would use the z-scores instead. So the process will be exactly the same. It's just that instead of using this standardized test statistic to find your p-value or your critical region, we would use z-scores. And then this is just, I want you to read the problems and ask yourself, what would you use? Would you use a t-test or a z-test? And then once you answer that question, would you use a t-test for 2 samples or a z-test for 2 samples or for 1 sample? And so this is kind of putting it all together so that you can practice reading a problem and be able to tell what is it that you're doing. Are you doing a 1 sample t-test? Or are you doing a 2 sample z-test? And so on. So go through it, and then if you want to know the answers, send me an email and I will share them with you. Or you can tell me, this is what I got. Am I correct? And I will respond. All right. Email me if you have any questions.